Okay, so let us go through method number one of dynamically assigning IP addresses, which is stateless auto configuration. It allows devices to configure a GUA without services of the DHCP. Devices obtain the necessary information from the RA messages of the local router. The prefix is provided by the RA, and the device uses either the EUI64 or a random generation method to create an interface ID. So what is happening here? If we have a Slack enabled router, so let's say this is my PC, then this is my router. If that router is enabled to configure IPv6 addresses to host end devices using Slack, then it will be sending RA messages on intervals. This device will be sending, let's say they are connected, this is the network. So it sends RAs at intervals. And in these RAs, there is information about the default gateway because the router knows the default gateway of the network is this. The network prefix, which is basically the network ID in IPv6. The network prefix is this. So this is the information that the RA message contains, being sent at intervals. Right. If a new device enters the network, device A, and it hasn't received an RA message, probably yapinda pa interval yekuti message ye-RA ayisati yasendwe ipapo. What happens is inosendawo rinonzi RS. If coincidentally kupinda munetwork rosangana ne-RA, then rinototangira kushandisa information iyoyo yakutoziva default gateway, yakutoziva the network prefix, yakugenerator the interface ID on its own, that device. If not, then it sends an RS, router solicitation. An RS is sent, then this router responds with an RA. So Slack basically doesn't work using DHCP version 6. And by definition, yakatonzi stateless auto configuration. Stateless basically meaning it does not track, there is no central server which monitors address assignment. With the DHCP, okay, if we can go to general DHCP, what is happening in the network? DHCP is giving IP addresses to hosts. So host A, this is your address. Host B, this is your address. Host C, this is your address. This server knows. So this is the DHCP server. It knows these are the IP addresses that I've given out. These are the IP addresses that I have left. So it is monitoring, it is tracking every IPv6 assignment in the network. With Slack, it does not do that. It is stateless, meaning it does not monitor. Why? One of the reasons it is stateless comes from this. Right, this is created, let's start with the random. Random, it is as it sounds. It's a random number which is created, a 64-bit number which is created. However, this prefix is the same for all devices in the network, but this one is just a random number which is created by the device. So every device has this unique number which is being created, therefore confirming a truth stateless because only the device knows that random number that is being created. Right. The other way which we can get the 64 bits for the interface ID is by using a not EUI64. EUI64 basically uses the MAC address, of the device. So this device's MAC address is used to come up with this 64-bit number. I think there's a slide which explains perfectly how that is done. So we have 48 bits per MAC address. You're supposed to know the number bits mangani. At this point, you know IPv4 32, IPv6 128, MAC 48 bits. So we have 48 bits the MAC address. We are only left with 16. Then there is some 16 bits which are added there. There is some gymnastics done with those numbers. That's how we come up with a 64-bit number, which becomes our interface ID. So Slack, I think it's very easy. It does not need DHCP device mirror. What it just needs is the default gateway and the prefix and the network prefix, giving an idea of which network do I belong to the host. I think that's Slack for you there. Let's move to Slack with DHCP. Starting up a Slack with DHCP, you can see the only thing that this network has, this host has, is the default gateway and its IPv6 address. That's it. Hapana DNS information, hapana any other information iri kupiwa kuhost. So you will see if we are in a very big network, or let me say application, where do you use Slack and only Slack in a network? We use it if we have a very small network where we don't have need yokushandisa DNS, for example, where we don't have need yokushandisa any other extra information in that network. So this one is very useful, very easy. Does not need a server. You don't need to have a DHCP server. So this is an easy way of dynamically assigning my IPv6 addresses, but it has its limits. Kana network yakura, you need that extra information, but with Slack, you don't have it. So that extra information can come from using Slack with a stateless DHCP server, basically. So with this one, an RA can instruct a device to use both Slack and stateless DHCP's version 6. The RA message suggests the devices use the following: Slack to create its own IPv6 GUA, the router link local address, which is the RA source as the default gateway, okay, a stateless DHCP server to obtain other information such as the DNS server address and a domain name. So with this one, basically, device binary network, I think this is our device. Binary network, it sends a solicitation message. There it goes. RS. I'm new to the network. I need I need an IP address basically. Then the router responds with an RA. With an RA, if we are using Slack plus stateless DHCP, this RA message contains information equity. One, we are using Slack and DHCP. Since we are using Slack and DHCP, it means I'm going to give you the default gateway. I'm also going to give you the prefix, the network prefix. Then for additional information, you need to use the DHCP server. That is the information in RA message. Yashika panapa, this one uses the prefix. Yovea Gazera its own IPv6 address. So prefix plus EUI64, that 64-bit number in over MAC address, then we have an IPv6 address. Then if it needs that extra information, it then requests to the server. I have an IP address already, but I need some extra information. What is the DNS information? What is the NTP server information? And that's how it gets that information. So this is stateless DHCP plus Slack, basically. So Slack, as it is per method 1 plus DHCP. The reason why it was stateless again is because server is not monitoring my IP addresses. Server Basararo is only to give extra information, your DNS server address and the domain name, your server, or any other domain name for that matter. So basically, Slack plus stateless DHCP, that's how it works. Right, the last one, stateful DHCP. So the stateful DHCP is the DHCP server doing everything. Stateful DHCP is similar to DHCP for IPv4. A device can automatically receive a GUA, prefix length, the addresses of the DNS servers from a stateful DHCP server. You can see the change from stateless to stateful. RA messages suggest the devices use the following. The router link local as the default gateway, a stateful DHCP server to obtain the GUA, the DNS server information, and any other necessary information. So with this one now, if an RS is sent from the device, this one, I need an IP address. The RA will contain the message you could for your IP address, for your default gateway, for any other information, contact DHCP server. Then message yashkapan this one will contact the DHCP server. DHCP server will respond with all the information that is needed. Why it's called a stateful DHCP is because it's now monitoring assignment IPv6 addresses basically. And I think in simple terms, those are the three methods how a device gets assigned an IPv6 address. All right, now to EUI64 versus randomly generated. When we are using Slack, we said a host create its own IPv6 address using 64 bits, which can be randomly created, or we can use EUI64. When the RA message is either Slack or Slack with this with Slack with the stateless DHCP, the client must generate its own interface ID. The interface ID can be created using EUI64 or randomly generated. Okay, we are through that. This is how the EUI64 process works. The random one, it explains itself. It's just a software which comes up with a random IPv6 address. The IEEE defines the extended unique identifier, uh, which performs the following: a 16-bit value, right? So, Tandamo mentioned that MAC address in 48 bits. There is an addition in 16 bits which is needed so that we have 64 bits, the interface ID. So the 16 bits value which is being added is that one. Obviously in hexadecimal, F, that's an hexadecimal number. It is inserted into the middle of the MAC address, 48-bit MAC address. The 7th bit of the client is reversed from binary 0 to 1. I think the correct word is flipped. It depends. Can I read 0 and end up 1? Can I read 1 and end up 0? So let's work with that example at NIR. How does it work? So this is our MAC address, 48 bits. This one. So this is the MAC address of the device. Yatura assign IPv6 address. We have 48 bits there. We insert FFFE at the middle. So pakati is right here. I think so. Ndo pakati apo between 47 and 75. Ndo pauya kuna insert kwachi our 16 bits there. And then to insert our 16 bits, we go and look at the first octet. First octet real here. Octet meaning the first 8 bits. So the first 8 bits is FE. F is 111, that is F. E is 1110. Right? And you look at the 7th bit. 7th bit here, 1, 2, 3, 4, 5, 6, 7. This is our 7th bit. It needs to be converted to 0. It needs to be flipped. So we flip this one. Let me see if we get no. Our was FC here. Our first octet was FC. Iri ranga ratachinjwa kudhara kuenda kuna FE. So I want to go from FC to FE and see how they come up with that. How they came up with that. So FC is 1, 2, 3, 4. Then C is 12. C is 12. A is 10. B is 11. C is 12. 12 is 1, 1, 0, 0. That's 12. So this is the first octet there. Then from the first octet, the 7th bit, this one is the 7th bit, is flipped. So if we flip that bit, we get a 1 here. Then we convert this back to hexadecimal, which is FE, because this is 8 plus 4 plus 2, 14, which is E. Double over FE arapoyo. And this is how a host can turn its MAC address to a 64-bit interface ID. All right, as you can see, this method, security-wise, it's a problem. It's not very much used, EUI64. Reasons being, if you know the MAC address, of a device, then you can easily come up with the IPv6 address. Security-wise, which is not very good. So that's the EUI64 process. I think it's very much easy. Let's go to next slide. Randomly generated. Depending upon the operating system, a device may use a randomly generated interface ID instead of using the MAC address and the EUI64. So this is as random as it sounds. It's just a randomly generated number, the last 64 bits. But the problem with this is, it's not a problem actually. It introduces something else, Panyaye uniqueness. It introduces yet not a duplicate address detection. Because if you look at EUI64 is using a MAC address, which is unique. So MAC address can be unique, therefore 64-bit digits will also be unique. MAC address is a unique number. So we don't have a problem. At no problem, you could do two devices in a network and with the same IPv6 address because the MAC address is unique. But with that random one, although the coincidence, the probability to know two random numbers, that probability, I think, maybe in networks is that huge. We don't take much chances. But those random numbers can be the same because this device, it will generate my numbers I. This device in a network, it will generate my numbers I. I'm going to generate the same numbers and we have more problems because we cannot assign two my IPv6 addresses to two different devices. My IP addresses, they need to be unique. So what happens? There's a process here, duplicate address detection. Was it explained in this one? I don't know. Yeah, let me see. Maybe remove slide. But if it's not there, okay, it's not there. It's not there. Let me just briefly go through duplicate address. I think takamboita somewhere. I think pakati ARP. When I is right. To ensure the uniqueness of an IPv6 unicast address, the client may use the process of duplicate address detection. So basically, when a device joins an IPv6 network and it has its IPv6 address assigned, sender enable solicitation in NS. So randomly generated 64 bits zappo, then we send an NS. And if you get a response of that NS, it means that address is not unique. If you don't get a response, then that address is unique. So basically, NSE, the target mark IPv6 address. NSE don't send what any IPv6 address you assign what device. So let's say our device you assign one IPv6 address. Let's just call it ABC. The destination IPv6 address gonna send what NSE. Send where is she? ABC. Meaning, if I want a response, then there is an APC which is being used somewhere. Basically, that's how duplicate address detection works. You send a message, what is IPv6 address, you order assign a device. If you get a response, it's not unique. If you don't, then that shows an address is unique, basically. And this is similar to an ARP request for its own address. It makes sense. If there is no reply, then the address is unique. I think we'll go through that. Dynamic addressing of IPv6 link local address. So when we introduced matrices, Eddie, we talked of two types of addresses mainly, the GUA and the LLA. Every device is assigned those two IPv6 address. So here we discuss how you can dynamically assign a link local address. Uh, the figure shows a link local is dynamically created using the FE80 prefix and the interface ID using the EUI process or a randomly generated 64-bit number. So with this one, my link local addresses, you see they have this in common. They use FE80. This is the prefix. It's common. Every link local based upon on FE80, it means that is a link local address. Then the last 64 bits, it uses randomly generated numbers or the EUI64 process, like GUA as well. I think the only difference here is this prefix. This network prefix, ku GUA inobva router. RA message, where in a prefix information. But for this one, it is known is FE80. Then the other 64 bits, EUI64 or randomly generated. Uh, I think we've gone through this already. We now know what EUI64 is. We now know what randomly generated numbers are. We can continue. Dynamic Cisco routers automatically create an IPv6 LLA whenever a GUA is assigned to the interface. By default, routers use EUI64 to generate the interface ID. Here an example of an LLA dynamically configured on the interface of R1. Okay, I think just a repetition of information is all here. We know what EUI64 is. We know in link local address, here's a prefix of FE80. We know what is happening here. If you see FE inserted Apple per address Apple, it basically means we're using EUI64, or it can be randomly generated as we stated before. Right, verifying. When we have assigned my IPv6 addresses, Edu, how do we then see? Yeah, verification, I think it's very important. I hope people are doing my labs. Verifying. Verification after you've made my configurations, it's very important verifying what you've configured. Patagaita system, Patagaita, the first two modules, module number 2, basic switch configuration and end device configuration. To show what you had done, there was a command and show running configurations, short show run. That's how you verify what you've done on a network so far. We also have show IP interface. Then in the interface brief, those are show commands which can show you my interfaces, my IP addresses which have been assigned to my interfaces. Or show interfaces itself, like this one, show interfaces. And also the interface right show. It just shows you the settings that is called per interface and only that. Point is learn to use my show commands. They are very important. Show commands you should know. But if I want to see information about routing, this specific routing protocol, if I want to see information about VLANs configured on my network, how do I show? In the ASA, they definitely start with show. They are called show commands. So to verify IPv6 configurations, you can either use show interface, you go to the interface itself, or if you just use show interface, it's not any interface specified. I think it will list all the interfaces to the router, or you can go to show IP interface brief or show IP interface itself, and you can see my IPv6 addresses which are assigned on the device. All right, multicast addresses. So we mentioned the issue to do with types of IPv6 addresses that we have. And we said we have unicast, we have anycast, we have no broadcast, but we have multicast, right? For multicast we also have types of addresses that we have. Well-known multicast addresses, 10 minutes. We have well-known multicast addresses, and we have solicited known multicast addresses. Looking at well-known multicast addresses, these are IPv6 addresses that are assigned and are reserved for predefined groups of devices. So these IPv6 addresses are predefined. They are known. Kuti ukaona FF021 no broadcast if ku IPv6. It says to all devices on a link. This is a multicast group that all IPv6 enabled devices join. A packet sent to this group is received and processed by all interfaces on the link or network. FF02 double colon 1. So that is a reserved address. Hakuna kumwe kwanoiwana, but for all nodes multicast groups. Then we have 02 all routers multicast group. If a device wants to communicate with all routers on a network, it uses FF02. So basically, those are well-known multicast IPv6 addresses. Akawanda, it's not only those two akaiswa apa. Akati one day. Now, looking at solicited node IPv6 multicast. With solicited node, addresses are used only for efficient communication with specific devices on a link. That's the main difference between my IPv4 and IPv6. There are times where you don't want to send a broadcast. You want to communicate with only specific devices in the network. In this case, from the name solicited node, tambotaura ne-issue yekuti ma-device they send an NS. An NS neighbor solicitation message. All devices that have sent NSs, they get a response via the solicited node IPv6 multicast. It's more specific. It's not a broadcast, but specific to devices that have solicited. Vakumbira ndo vanopiwa. Basically, that is what solicited node IPv6 unicast is. Let me go through the text. We might get lost. A solicited node multicast address is similar to the all nodes multicast address. A solicited node multicast address is mapped to a special Ethernet multicast address. The Ethernet NIC can filter the frame by examining the destination MAC address without sending it to the IPv6 process to see if the device is intended target of the IPv6. Let me try and figure out a way to explain what IPv6, what solicited node multicast is. Let me try to find an example. Right, let me use an example ARP. ARP in IPv4. Then we have neighbor discovery in IPv6. These two protocols are used, so this is also called the neighbor discovery protocol. These two protocols are used to identify, to map the MAC address provided IP address of a device. But the processes, they are very different. In ARP, you see we send a broadcast, the request. So every device in the network processes that message, then some drop it and only one device responds. I repeat, in ARP, a broadcast is sent. The traffic yacho is actually sent as a broadcast. Multiple devices. If we have 1,000 devices in the network, then we have traffic here, 1,000 devices being broadcasted in the network. My devices processing that, then some of them dropping them, only one responding. That is not efficient. That message should probably be sent to that one device or should be processed by that one device process. The difference with NDP, for example, in how solicited node multicast works. So solicited node multicast, it uses, so let's say, for example, I want to find the MAC address of a in the network, let's say A, B. Is that practical? A, B. Let's say I want to find numbers. Numbers. This is an IPv6. Can I have an IPv6? I'm too lazy to write the whole number of hexadecimal values that present the IPv6 address. But let's say we have an IPv6 address. Let's call it AB. We want to find the MAC address of AB. What Neighbor Discovery Protocol does, it takes part of the IPv6 address, the last 24 bits to be more exact, last 24 bits. It takes the last 24 bits of that IPv6 address, then ndoineta address target mu NS redu, for example. Pa NDP, pa network exchange ye NS ne NA ndo response. So NS iri parinoenda iri rinenge rine part of the address iri pa destination. Inenge iri part of IPv6 ye device riri kuda kurequestwa racho. So if we have two devices, I'm requesting the MAC address of this device. So this device is IPv6 address. The last 24 bits ndozonotorwa dziiswa pa destination ye frame or packet frame actually rinosendwa ne-NS. How does that help network? It means it becomes very easy for my devices to process kuona kuti message ndeyangu because they will just look at these 24 bits and be able to identify that this message belongs to me. So instead of sending a broadcast to all the devices, we send a multicast the solicited node. Only node or a group of nodes dzine this specific last 24 bits ndodzinotaggetwa chete, significantly reducing the amount of traffic inenge iri munetwork. So instead of sending a broadcast, we send more of a targeted multicast inosvika exactly per device because of the nature yes solicited node multicast. It's making sense in my head. If it's not equal on the other end, I think you can repeat this, then add with a little bit of research. I think it's no fun link. But basically, the easiest way to understand is using an example ARP and NDP. ARP send a broadcast, creating traffic yakawanda network. This one, I send a broadcast. Send a multicast. The solicited node here. Then only that node or only that group of devices responds to that. All right, let's continue.